Hello, this is MEI Further Maths Core Pure. We're in the second matrices section and on the sixth and final video on invariant lines and points. You can watch the video straight through, but you will probably find it helpful sometimes to pause the video and try things out for yourself before continuing to watch. When we apply a transformation matrix to a point, it creates an image of that point. For example, if we take the matrix 5, 2, 4, 3 and apply it to the point 1, 2, doing the multiplication we get 5 plus 8 is 13, 2 plus 6 is 8. So the point 1, 2 is mapped to the point 13, 8. Sometimes though, the point doesn't move. For example, if we use the same matrix but apply it to the point 2 minus 2, we get 10 take away 8 is 2, and 4 take away 6 is minus 2. So the point 2 minus 2 is mapped to itself. We say that it is an invariant point. It doesn't vary. What happens to the origin under a matrix transformation? Pause the video for a moment while you think about that. OK, let's take any general matrix A, B, C, D and apply it to the point 0, 0. Of course, we get 0, 0 again, because if we multiply by a zero matrix, we get 0. That means that the origin is always an invariant point under a matrix transformation. How do we find invariant points? Well, let's take that previous matrix as our example again. 5, 2, 4, 3. We want a point which isn't going to move, so let's just take a general point and say that it doesn't move. This gives us a pair of simultaneous equations. 5x plus 4y must be equal to x, and 2x plus 3y must be equal to y. Tidying them up, we get 4x plus 4y equals 0, and 2x plus 2y equals 0. But these are both the same equation. X plus y equals 0. We can't find particular values of x and y, but in fact we've got a whole set of values of x and y. Any pair of values that satisfies this equation won't move. For example, 5, 2, 4, 3 multiplied by 5 minus 5, x plus y equals 0 there. 25 take away 20 is 5, and 10 take away 15 is minus 5. Every point on this line remains stationary. It's a line of invariant points, and it has the equation x plus y equals 0. Let's have a look at this in Geogebra. OK, here I've got the matrix 5, 2, 4, 3 as before. I've got a point here P, and its image is P dashed. P is attached to the brown line, and the green dotted line is the image of the brown line. I can move my lines around, and if I get the line x plus y equals 0, then you can see that every point on this line gets mapped to itself. P and P dashed are on top of each other. In the last example, we had a line of invariant points, but sometimes a line is mapped to itself by a transformation, but the points on the line are not mapped to themselves. Here's another example of it in Geogebra. Here I have the matrix 0, 1, 1, 0. Again, the green dotted line is the image of the brown line. If I change the brown line so that it's the line x plus y equals 0, you can see that the line maps to itself, but individual points don't map to themselves. This point P on the line maps to another point on the line. The only point that remains the same is the origin. The matrix in that example was a reflection in the line y equals x. Pause the video for a moment while you think about which lines you would expect to be invariant in that reflection. OK, let's have a look at it. In a reflection, we expect the mirror line to be invariant. So if I plot the mirror line, y equals x, you can see that this is in fact a line of invariant points. Points on the mirror line are mapped to themselves. But we also saw that this line was an invariant line. The further away the points are from the mirror line, the further they move, but they're always on the line. This line is perpendicular to the mirror line. If I move it to another perpendicular line, then it remains an invariant line. All lines perpendicular to the mirror line are invariant lines, but they're not lines of invariant points. Only the mirror line is a line of invariant points. There are more notes on integral on invariant lines and points. That's the end of this short video and the end of this section.